Thank you for the introduction. So I'll try to summarize briefly a whole lot of content which was in track 2. Right, it was a really fantastic. Oh wait, I do need this. Thank you. Okay, so just some brief statistics. Right, so in track 2, we have 33 talks out of 90-some abstracts submitted, 26 posters, results from many collaborations. I counted 13. I might have missed one. I apologize if that happened. So you can see that there's a lot of this is really used all over HEP. Obviously, we analyze data, but given the focus of this conference, right, which is on, it was nicely reminded, is on cats, right? And you do remember that one of the fantastic machine learning accomplishments is to distinguish cats from dogs. We should really think of thematics for things. So in this particular conference, we did want to focus more on machine learning. So as a result, there was a significant proportion. I think roughly about 70% of the material actually was on machine learning. So we really got a good idea about what's happening in the field in machine learning and how it relates to data analysis. So that's the overall statistics. And what I'm not really mentioning here is the things you saw during the plenary sessions, because there's a number of talks during the plenaries related to deep learning, machine learning, et cetera, as well as a panel discussion. So that you hopefully already saw in the plenaries. The main topics were, really, I would group them into 2 areas, which is the algorithms and their applications in particle physics. So that could be the physics itself, the object ID, reconstruction, tracking, trigger simulation, the list goes on and on. Lots of applications. And the other part, which is basically the tools that you need to do it. And not necessarily just for machine learning, but basically also analysis tools for other things like simulation, general purpose tools, fitting, visualization, et cetera. So that I would group things this way. And within those groups, if you look at the machine learning applications, there's a lot of interesting things. I want to highlight the work shown here by CMS in particular on you basically doing this end-to-end learning, which looks into comparing some of these approaches to some of the more traditional reconstruction, but treating your detector as an imaging camera with many other things with that. So basically trying to pose the problem and see whether the deep learning methodology can extract features and do some really useful things for you with some good initial results. And you can see the theme. These guys are really popular, right? So these imaging techniques from computer vision are really taken off in particle physics. So you can see example from Microboon, a number of different examples which show so you can use this not just in one type of experiment and situation. The other interesting, this was a talk by Kevin Vierman, and then in another talk by Luke De Oliveira and collaborators, they showed us how to use some of this generative adversarial networks and also use this generative models for the purpose of simulation with good results. There's some things to be overcome. This is not yet the way to do things, but there's progress being done, and there's still a lot to be understood. But it's a very promising direction. I encourage you to have a look at the talk to see all the really latest results, including some of the things I think which were shown for the first time at this workshop. So that was quite exciting. The other things were actually there was a number of these results really I've seen for the first time in public. So outside of the collaboration, so that was really exciting. So one of the things was actually applications for tracking. For looking for different seats, and talk by Felice Pantaleo from CMS in particular. So looking for basically, again, applying some of these similar techniques from computer vision, but then for identifying specific patterns within specific detectors, and then doing things more in this way as opposed to some of the traditional reconstruction with some pretty good initial results. All of these are mostly R&D, but hopefully this will be something really useful in the future. This is a cross-inter-experimental project, HapTrackX, which actually uses a different type of architecture, recurrent neural networks, LSTMs, and for basically building up tracks, and some initial results are also quite good. So there's a lot of work happening in this direction. As you know, tracking is a complicated problem, right? You have a ton of channels, and so this is relatively a sparse problem. Here is also well suited for machine learning, where it can actually have a big impact. And another interesting talk was by Eric Metodia on removing pileups. So just to give you a breadth of applications, basically. And some of these are really similar. You may say, well, are these all just convolutional networks just thrown at something, right? So many times actually depends on how you pose the problem and how you set it up. There's a lot of details that go into how you do it, right? And your results are coupled to that. So if you just say, hey, I have a problem, I'm going to throw my convolution over, it doesn't always work. So you have to figure out how to do this. There's some engineering work and actually some art, I would say, as well, so on how to do this. And but there's something interesting in this talk is also on the part that has to do with interpretation of the model. So I would encourage you to have a look at the details. Some nice results comparing this method to some other machine learning methods. And what's interesting also to note is that some of the machine learning methods that we use today, right, and the variants that thereof are different from what were used maybe 5 years ago or before that, right? And the way that, and we also compare them with some of those other methods and other applications. Really the movement is towards putting in some knowledge of the problem in some cases in the setup of the architecture of the problem and so forth. So combining basically physics and machine learning. That I think is quite interesting, and was pointed out I think in a talk by Kyle at some point. There are some results from Atlas on B-tagging, again, using some of these techniques in different parts of the chain with some pretty good results, including both the deep learning ones and recurrent now with STM, all the bells and whistles, I think, in this application for B-tagging, and the corresponding CMS results on flavor tagging. Again, using all the bells and whistles, really. So CNN is really a major component of this particular result. But the results are very, very impressive. So there's improvements across the board, not just in B tagging, but in flavor tagging, meaning with B from C. It's basically a single tagger. It seems to do really, really well, so, which is learned again from a deep neural network, not necessarily a million layers deep, but sufficiently deep and sufficiently powerful. With physics ingredients, right? Physics-inspired network. There's some components from particle. There's interesting ideas in this work, and the results are quite good. So you see significant improvements, especially in places like high momentum, where you have some issues, and it really outperforms not just the traditional B-tagging. It actually outperforms other variants of machine learning. So this is a very interesting result on application of deep learning to this particular problem. And again, this is starting to be used in real analysis with good impact. So this is a nice result from CMS, out public, I think, for the first time officially. Now, up to now, you say, well, it's mostly just deep neural networks. So it's not really the case. There are other algorithms which have been powerful and used as well. So for example, this XGBoost algorithm, which is more relevant to boosted decision trees, was an application shown by Microboon actually when looking for, when looking, again, this is a multi-class setup, which is really something which you see here and again. So as opposed to training, a single algorithm, and algorithms to do specific things. You actually try to, when you have multiple classes, you can actually make one model to do it. And this particular one looks at for protons and how well you efficiently to find them, and uses this particular variant of boosting algorithm applied to decision trees, which seems to work quite well. It's quick, and this is just one application, but it really has taken off as well. There are other results based on that. Applications to the trigger. This is quite a hot area. And you can see, for example, on top here, this is already in the trigger of CMS, meaning the software and the hardware trigger. Level 1 is the hardware trigger. So here you see a reduction of the rate for muon identification, and basically uses FPGAs and boosted decision trees for regression. It's also on the software side. There's another. This was a talk by Andrew Carnes, and then another talk by Sebastian Ambrex, and this is from Bell 2. This is neural network-based model, which seems to be doing quite well as well in a trigger. And LHCb as well. They presented this idea of tensor, basically kind of like a decision tree tensors, and their applications and speed up of the trigger as well, which is on some figure of merit and the number of lookups and how much time it takes, and it's very promising results as well. Something called CAT boost. And The other quite interesting talk as well, more on the interpretation side, tries to answer a very simple question, right? Can neural networks, can deep learning, what is the complexity of it needed to learn some of these physics observables that we particle physicists use all the time, meaning invariant mass, momentum, energy, and so forth. And this nice talk, you saw, and it actually tries to answer this question: can you throw 4 vectors at a neural network? Can it actually figure out those things, right? And this is a very neat question, and it shows in a couple of cases of z to mu or dt bar to mu that indeed you are able to learn something useful, meaning some functions of your, the x and y in this particular case of transversal momentum, and it does really well in estimating, right? In estimating the momentum. However, in the case of invariant mass, you need more complexity. It doesn't do as well, so there's still more to be understood. But even in this simple question, it seems to perform well. And so this goes along trying to understand: can we figure out what exactly is being learned? Right? It's an important area. So I really like this particular talk by Kati. And yeah, so that's basically a highlight. I didn't mention everything. Obviously, there's no time to do that, but just a few highlights. On the analysis tools, I'll just move over to this side. There's some news from Root, right? So on different things on parallelization, vectorization, math, I/O, graphics, moving to the browser. You can see talk by Axel. And also something which was mentioned quite a few times in this talk, and also there's also this new sort of idea of T-data frame, talked by EM Amadeo, and which is basically just a different way of interacting with the data, and less code, and also easy to parallelize, and show some example speed ups for for a 16 cores, get about 12 times speed up, which is pretty good. The box, and this idea is really, you can see across the board. Parallelization is important. People care about time, how much things take, how easy it is to write and maintain. So this is I think was highlighted in the presentations from the SMT team. And the other nice talk was by Oliver Guccio that shows how do you apply, how do you go through the exercise of speeding up doing your analysis and reduction and filtering of everything you're doing to get to your histograms, in this case using Apache Spark, another tool developed by Diana called Histogrammer, which is just a different way of to do this map reduce operation on histograms, and with some results already. So quite a promising thing. There's a nice talk that you can have a look at. And there are other tools which were shown, which are quite interesting, updates on GoofIt, optimizations of Geant, other tools relevant to deep learning and delivery of deep learning to your computer clusters and whatnot. Again, Cat Boost and virtual reality tools and visualization and interpretation and of the analysis. So that's sort of the overall summary. And just want to thank really all the presenters, attendees, panelists, really everyone who participated. I think it was a really, really enjoyable session. I learned quite a lot and really got the idea of where the state of the art is in ML today, particle physics. So with that, I'll conclude. Thank you. Yeah.